everybody. Welcome back to the channel. I am Professor Parks, and this morning, I'm recording this at 5 in the morning. I believe I've got one. I think Nerd Alert, you're in the audience. Hi, good morning, good evening, or good night, wherever you may be. This is Professor Parks, Fairfax County, Virginia. Anyway, so this lecture is going to essentially be a wrap-up of what the lecture I did last time, which was talking about the moon, specifically the phases of the moon, how the phases, why do we see these phases, when do we see these phases, that sort of thing. So I know in the description of this video, which I'll probably change, I say I'm going to talk about the formation of the moon, and actually, when I'm reviewing my schedule, I noticed that I'm actually going to talk about that later on. So today, I'm going to try to have a little bit of fun and talk about the moon in terms of eclipses and tidal forces. So, if any of you were wondering, the globe that I have on my bookcase back there is not the Earth. It's actually the moon. Yes, this is my moon globe. Why do I have a moon globe rather than an Earth globe? Don't know. Never figured that out. Just seem to have one. So yeah, I'll be referencing this later on when we actually start talking about fun things like craters and morae and stuff like that. So, where do we leave off? Let's see. I think I'll just start this. How about that? Aha! Oh, then I will present entire screen. That one. So hopefully you all can see this. So this is really just going to be a summary or summary of the last lecture. So what we found was that the reason why we have phases of the moon is because of simple geometry. We have the situation where we have the Earth, we have the moon going around the Earth, and the Earth is going around the sun. And so in all cases, at all times, both half of the Earth is lit up, half of it is in darkness. So half of the Earth is experiencing daytime, half of the Earth is experiencing nighttime. And the same is true about the moon. But because of a thing called tidal friction, which I'll go over in a moment, the moon actually happens to show the same face to us at all times. And so when we look at the moon, the portion of it that we can actually see, or the lit up portion of it, varies because of where it is in our particular, where it is in relation to us. So here's the 8 principal phases. We have new, waxing crescent, first quarter, waxing gibbous, which apparently means hump in Latin, full moon, waning gibbous, third quarter, and waning crescent. So again, it all depends on our perspective angle to the lit side of the moon. The last thing I talked about, or the thing that I talked about last time, is the synodic period, or the synodic cycle, or the lunar cycle, the difference between a synodic period, a synodic month, and a sidereal month. So this is, I think, a much better way of looking at it. So what we have here is we have, obviously, the Earth and the moon on the left and the sun on the right. And we have that the Earth is, hey, Jezza, wow, howdy, I haven't seen you in an age. So we have the orbit of the Earth is prograde, or is counterclockwise as viewed from the north. So is the orbit of the moon. It is counterclockwise when viewed from the north geographic pole of the Earth. And so what happens is, again, in order to get those phases, the moon is going to be orbiting around. So when we have a new moon, the orbit of the Earth, or excuse me, the moon is in the same direction as the sun. It's not in between specifically, but it is simply in the same direction as the sun. Now it takes the sun it takes the moon only 27.3 days in order to make that one loop around the Earth, to actually complete one circuit around the Earth. And that is what we refer to as the sidereal month, or the period of time it takes the moon to essentially be it'd be Earth, Moon, distant stars, and then have it go all the way around, and then have Earth, Moon, distant stars. Then we have the synodic period, or the period with relation to the day, or excuse me, the period with relation to the sun, and that is 29.5 days. The reason for that is because, as I said, as the moon is orbiting around the Earth, that takes a little bit of time, and during that time, the Earth is moving itself around the sun, and so the geometry changes, and so the moon has to move a little bit further along in order to get back to a true new phase. So after 27.3 days, what we would actually see is that the moon went from a new moon to a waning crescent. So it takes another couple days for it to come back into the new phase. So let's talk about eclipses. I'm actually very excited about eclipses because we're getting two pretty. If you live in North America, next couple of years are going to be really, really cool. At least in terms of the sun. So, what are eclipses? Eclipses are a phenomenon that has been traced back thousands of years. We have been observing eclipses pretty much and writing it down that we've seen these eclipses for a really, really long time. And for a really, really long time, these eclipses kind of freaked people out, particularly solar eclipses. An eclipse is when the light emanating from either the moon or the sun gets blocked partially or blocked entirely. So you can imagine if you are ancient peoples, as it were, if you're like in ancient Greece or in ancient China, then having the sun suddenly go out for about 4 or 5 minutes is probably going to mess you up. It's probably going to be really weird you out. The rest of your day is probably going to be a little strange. So one of the first things that the people in charge did was try to figure out, tell people, hey, tell me what's going on here. That way I can warn people that this is going to happen. And so through just basic study of these past events, and the astronomers of old were able to come up with predictions about when this was going to occur. These predictions have since been perfected? No, refined. And so now we have a very, very good and very, very good understanding of what causes eclipses, when eclipses occur. So you've got two major types. You've got a lunar eclipse, and that is when the light from the moon appears to go away for a short period of time. And then you have a solar eclipse, where the light of the sun appears to go away for some manner of time. Both of these essentially are caused by shadows, that you have these physical objects in space which cast shadows based on the light from the sun emanating in our direction. So in the case of the moon, or for lunar eclipses, what occurs is that the moon, as it travels in its orbit, is going to occasionally pass through the Earth's shadow, and that's going to affect the amount of light reflected off its surface, and that's going to cause it to go into an eclipse. Consequently, when the moon comes around the other side, occasionally the moon will actually pass in front of the sun and create a shadow of its own. And that shadow will then appear on the Earth and will travel across the surface of the Earth. And those people in that shadow or underneath that shadow will see that the sun is blocked to one extent or another. And that is a solar eclipse. Now, there are a few different types of eclipses. I really need to work on my slides. The first, let's see here. The first type of eclipse, or let's look at lunar eclipses. So if you look at this diagram on the left, on over there, you'll see on the top one that a shadow, particularly at these distances, you can kind of see this effect locally, but over large distances, a shadow is going to have two parts. The first part is called the umbra, and that is the darkest part of the shadow. What that means is all parts, if you are in that position, no light from that from the sun or the light source is going to hit you. You have effectively blocked out all of the photons coming from that from the sun. If you're in the penumbra, what that means is some portion of those rays, some portion of that light has been blocked, but not all of it. And so you have a dark portion, the umbral part, and then you have the lit or a lighter portion, which is a penumbral point. And so that leads to three types of lunar eclipses. The one that we are probably that's most dramatic is a total lunar eclipse. Now, a total lunar eclipse occurs when the moon passes through the umbral part of the Earth's shadow completely. All of the moon will be in the shadow at some point in this sort of trajectory, as it were, and it then moves out of that shadow. So first it moves into the penumbral region, so it'll dim a bit, and then it'll move into the umbral region where it will essentially go away or appear to go away. And then it will come out of the umbral region, get into the penumbral region, and then finally leave entirely and brighten up a bit. Then you can have, so that's total. Then you can have partial eclipses. A partial eclipse is when the moon, only part of the moon passes through the umbral part of the shadow. So maybe the top half of the moon gets blocked. All of the light for only the top half of the moon gets blocked as the moon is passing through space. And then finally, you have what is known as a penumbral shadow. I have to say, penumbral eclipse. I have to say that these are sometimes publicized. I have yet to see a penumbral eclipse where I actually noticed a difference. A penumbral eclipse is when the moon passes only through the penumbral part of the shadow. No part of the moon gets blocked by the umbral, the darkest part of the Earth's shadow. Technically speaking, it does dim, but it doesn't dim by a whole lot. And so if someone out there has seen a penumbral eclipse, actually seen it dim a little bit because of this effect and then come back out of it, you are a better person. You have better eyes than I do. Because I have never seen that effect. But technically, that does happen. The moon will pass through the penumbral part of the Earth's shadow. Now let's talk about solar eclipses. Solar eclipses, there are three of those. There is total, there's partial, and there is annular. Now, total is when you are I'm really not happy with these slides. I'm going to see if I can find better ones. Solar eclipses. I know this is very, very professional of me, but let's go with that. Let's go with that. All right. I am going to stop sharing that screen. I'm going to share Hmm? Where is it? Where is it? I have so many tabs open. I've been doing so many high IQ research. There it is. Share. And no, don't sign me up at all. So here we go. Well, that way I can have a cursor. Howdy, Norm. So again, we have essentially we're going to have three types of eclipses. We have total solar eclipse, a partial solar eclipse, and what we call an annular solar eclipse. Now, there is a significant difference between a lunar eclipse and a solar eclipse outside of the fact that, um, one is the Earth shadow blocking the moon, and the other one is the moon shadow blocking the sun. The key difference is that if a lunar eclipse occurs, if you could see the moon at that point, wherever you are on the planet, if the moon is in the sky for you at that time, when that eclipse occurs, you can see it. So a lunar eclipse can be viewed by a whole lot of people simultaneously. A solar eclipse, not so much. A solar eclipse, a total solar eclipse, I should say, is not viewable by a huge amount of people, which makes it a little bit more special. Which is why, if you ask just random folks, they probably will tell you, "Yeah, I've seen a total solar or total lunar eclipse, but I probably haven't seen a solar total eclipse." I would fall into that category. I've seen half a dozen total lunar eclipses, but I have never seen a total solar eclipse. That is because here, the moon's shadow, the umbral part of the moon's shadow, does not encompass the entire surface of the Earth. It only encompasses a very small portion, roughly about 50 miles in width. That changes based on the geometry of things, but on average, the width of the shadow as seen on the Earth of the moon is about 50 miles in extent. That is the umbral part. If you're underneath or in that shadow or underneath that shadow, you will see the moon move all the way in front of the sun, eclipse the sun. Everything will go dark for about 4 minutes or so. I've heard it's actually a rather kind of transcendental experience. And then the moon will move out of the way and the sun will come back. And apparently the birds and the night creatures that had come out will suddenly freak out and be like, "Wow, why is it day so sudden?" And they'll run away. And so that is what we call, that is a total solar eclipse. For a larger portion of the population, they will see what is known as a partial solar eclipse. They will see, if they're in the umbral part of this region, what they will see is they will basically see only part of the moon cross in front of the solar disk, and so only a little bit of the light is going to be blocked. So very much like a partial lunar eclipse, where only part of the moon goes away, it goes completely dark. A partial solar eclipse is when when only part of the sun goes away. Then you have annular eclipses. As I mentioned last time, I showed an image, or I showed a simulation of the moon's orbit around the Earth using Universe Sandbox. Great program if you don't have it. Highly recommend it. And if you look at the orbit of the moon, it is significantly, or noticeably, I should say, noticeably non-circular, meaning that it's elongated, it's elliptical. The consequence of that is that at some portions of its orbit, or some points in its orbit, it's going to be closer to the Earth than it is on the opposite side of that orbit. We refer to this as perigee, when the moon is closest to the Earth, and then apogee, when the moon is furthest away from the Earth. If the moon happens to be near apogee when this eclipse happens, then what occurs is that the moon is no longer roughly the same angular size as the sun, and the moon will be a little bit smaller. And so, if you're in the path of totality, or annularity, as they call it, what you will see is that the moon will go in front of the sun, and then it will get into the center of the sun, and you will see this ring of light around the outside of the moon. Nope, that's not the right one. That's the right one. Annular solar eclipse. You'll see something that looks like that. Oh, no, wrong page. Wrong one. Stop sharing. Share screen. That one. That one. So on the right or on the left, go away. On the left, this is a total solar eclipse. On the right, this is a partial solar eclipse, and then in dead center, that is an annular solar eclipse. That is when the moon is at close to apogee, is further away in its orbit than it is ordinarily in the span of the lunar month, as it were. And so the moon's angular size is a little bit smaller, and so it doesn't quite block the entire size of the sun. And so you get this nice annular shape around it, or a nice annular ring around it, or a nice bright ring around it. Annular ring is kind of redundant. I should point out I should say at this point that it's sort of a happy coincidence that the angular size of the moon and the angular size of the sun are nearly equal to each other. They're both about half a degree. Again, the moon's angular size is going to change, and so does the sun to a little extent, because the Earth is also in an eccentric orbit. But that doesn't change nearly as much as the moon does. But it's really just kind of a happy accident that the moon happens to be the same angular size as the sun, meaning that the sun is 40 times further away than the moon, and it is 40 times, is that right? 40 times larger than the moon? I think it's 400. I think it's 400. Anyway, I'll look that up. But it's a happy accident that those two happen. Now, at this point, what I'd like to do while I open something up is I am going to ask the class 2 questions. First question is, what phase of the moon does the sun? What phase does the moon have to be in order for a solar eclipse to occur? That's question 1. What is the lunar phase that must be in order for a solar eclipse? Well, let me flip it around. When a solar eclipse occurs, what is the phase of the moon? First question. Second question. What is the phase of the moon when the lunar eclipse occurs? And in both cases, the phase is different, but in each lunar eclipse, the phase of the moon is the same for every lunar eclipse. It has to be. And the same for the sun. I think Earth is Life beat out Jezza just barely. But yes, you guys are correct. For a new moon or for a solar eclipse, the phase of the moon must be new for that to happen. For a lunar eclipse to occur, it has to be full. So essentially, the orientation you need is for a solar eclipse, you need the moon in the way, meaning that you need the moon in the way, which means that it has to be the new phase, and then the opposite for the lunar one. So let me show you this. So, like I said, in North America, we are. It's going to be kind of an exciting time in terms of solar eclipse solar eclipses. In October 14th, 2023, there is going to be an annular solar eclipse, which comes in from basically Oregon, comes down through the continental southwest, goes through Texas, and goes out through the Gulf of Mexico. This up here is what we call the path of annularity, as it were. And then that is October 24th, 2023. And then about 6 months later or so, you have an April 8th, 2024, you have a total solar eclipse coming in from Mexico, from basically the state of Durango, I guess, Mexico, coming up through Texas again and going out through Newfoundland. Now, let me show you. Here we go. Yeah, there we go. So, what was I when I was talking about? Hey, I'm going to talk about that in a second. There, Earth's Life, about where I'm going to be for these eclipses. So here's a closer map or a closer look at who will see what. And so this path here, or this orange band, is what we call the path of annularity. If anyone is located or living or happens to be on the United States where this path is, they will see an annular eclipse for some amount of time. If they are outside this line, you can see these lines here. This corresponds to an 85% partial solar eclipse, 80%, 75%, so forth. So almost all of the United States, except for possibly the Northeast, is going to see, or has, if it's clear, is going to have the ability to see a partial solar eclipse on October, 18th? No, it's right there, October 14th. But if you're in here, you will be able to see an annular solar eclipse. Now, if I can read this correctly, yes. The time of totality or annularity, the time that the moon is going to be in a position where it blocks out most of the light and you have this nice ring that you can see, is approximately 4.5 minutes if you're dead center. If you're off to one side, to one or the other, the amount of time that it stays in that annular eclipse phase is going to decrease, and it's going to do so rapidly. I don't know exactly what the mathematical functional term is, but you move a little bit, you're only going to shave off a few seconds. But if you get closer and closer, you're going to start shaving off minutes. So you want to get as close in the middle of this as you possibly can. So you got this. You might be wondering what the circle is. That blue circle represents what the shadow's extent at that specific instant in time. So the shadow is not a sphere, the shadow is not a circle passing across the surface of the Earth. It actually is oblong because again of the geometry, the fact that the Earth is a sphere. There you have basically this bending, not really foreshortening. I think that's the correct term here. Is you have this foreshortening of the circle. Basically, it gets longer in one axis than it does in the other. And then as the shadow gets closer and closer to the center of the Earth, or not quite, but closer and closer to kind of like the central or sub point, the point directly beneath the sun, the shadow becomes more and more circular. It's actually one of the niftier kind of illustrations of why the Earth is a globe, which I likes. So you got that. I won't. Now let's look at the solar eclipse. Actually, here we go. So annular eclipse. This is the website. I'm just going to go to, here is, copy. If you want to know more about this stuff, and you're excited about this as much as I am, here's the eclipse for the information for the solar eclipse or for the annular eclipse. This page is awesome because it gives you maps by state and regions and things like that. So if you want to experience this, you can plan it out. But I'm going to kind of skip ahead and go here because the solar eclipse, the total solar eclipse, is actually going to it's going to pass across the Earth or pass across North America in sort of a complementary direction to the point that they're going to cross. So there is a town. Oh yeah, use proper protection. Actually, let me do this. If you want to know about the 24th, this is the copy. If you have trouble getting proper eye protection, which you can do here, hit me up, email me. I will email you, or I will mail you Eclipse glasses for free, free of charge, free of shipping, anything. If you want Eclipse glasses, talk to me, and I'll hook you up. So before I get into the exciting bit, here again is the basically the solar eclipse. That's the total solar eclipse that's going to happen on the 8th of April. And you can see that this is the path of totality. And very much like I was saying before, if you're near the center of the path of totality, you're going to have roughly 5 minutes where it's, it's roughly 4.5 minutes of darkness, of complete darkness. And you can see basically that time. This is showing actually this GIF, as it were, is showing a very good representation of how much totality you will see if you're in that certain portion. If you're outside of this band, you will see again partial phases. You will see the solar eclipse as a partial or some fraction of it, 80%, 70%, and so forth and so on. But yeah, so let's go here. Going back to this one, share this tab instead. Yes. Right there is a little town called Leakey, Texas. Leakey, Texas. Bam. So share this tab. So there's San Antonio. We go to here. San Antonio is right there. So on Google Maps, I think we're roughly around here. So this is the largest town that I have found that is close to the center lines for both the annular eclipse and the total eclipse. And so this town has a population of 425, 426 on those dates. What I want to do is, and I'm going to post an entirely separate video about this. What I want to do is I want to be there in the same location for both events, and I want to record them, maybe even live stream them. And that way I have, as a good scientist, I have essentially a repeatable experience. I have controlled all of the variables. That way I can truly compare what an annular eclipse looks like compared to a solar eclipse, because I will be in basically the same location for both. The timings are going to be a little bit off. I think the annular eclipse is actually a little longer than the solar one, but like I said, I'm going to make an entire video about that stuff, and that's going to be coming out within the next month. Because, like I said, this sort of thing you got to plan for early. There are a lot of crazy astronomers out there, and they book up hotels a year in advance to make sure they got their own spot. So yeah. Now, you might be wondering, like Sleeping Warrior wondered, why don't you see eclipses all the time? Why is it that Because, like I said, or as you pointed out, as you folks rightly pointed out, a lunar eclipse occurs when the moon is full. So the natural question is, why is it that not that the eclipse doesn't happen every full moon? Why doesn't a lunar eclipse happen every full moon? Consequently, why is there not a solar eclipse every new moon? Well, I got toys. I got props. All right. So, where did my moon go? Ah, there it is. All right. Prop number one. This is the Earth on drugs. I'm sorry. 80s commercial. This is the Earth on a stick. To scale, this is the moon on a stick. So, you'll have to take my word for it, but basically, these two are roughly the same distance away from the camera. So that's the size to scale of these two things. All right. This is a meter stick that folds, which is really cool. It's really awesome. So what I'm going to do is, I think I'm having way too much fun with this. All right, let's go here. Aha, Earth. There we go. All right, so all right, so again, we've got the Earth. We got the Earth, we got the moon. Now, we want Earth of Life. You're getting ahead of me. Yes. Spoiler alert. It's because of the moon, because of the actual tilt of the moon. Anyway, or the lunar orbit. Anyway, getting ahead of myself. So, we got the Earth, we got the moon. If we want to keep everything to scale, we got to move the moon further away. We got to keep moving the moon further away. Further away. Further away. Further away. It's getting pretty far. Further away. Further away. Yep. It's keeping going. Keeping going. And stop. That. Let me tack this down. Oh, shoot. Yeah, definitely having too much fun with this. That is the scale. So, with an Earth that size, the moon would be that size, and the distance between them would be 30 centimeters apart. So, that's the sun. So the Earth is going around the sun, like going around. If the sun is over here, then the Earth is going around the sun, and the moon is orbiting around the Earth. Like that. So, what this is trying to illustrate is to get that. Well, actually, say my head is the sun. To get that alignment, so that you can, so that I guess, no, I'm sorry. Let's look at it this way. You, the people in the camera, are the sun. So in order to get this alignment so that the moon passes right by, the tilt of the orbit of the Earth and moon relative to the tilt of the Earth around the sun can only be, if it's off just by a little bit, like this, then it's never going to happen. It's going to go above or below. Well, let me take that back. If it's off by just a little bit, then you're not going to have eclipses every single lunar full moon, every single new moon. So the angle right there is really, 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 really tiny. I hope you can see from that. And then this way, this would be kind of the lunar eclipse version of it. Again, this tilt, the tilt of this orbit cannot, if it's just slightly off from the tilt of the orbit around the sun, around the sun, then you're not going to have eclipses every single month. And as Earth is Life pointed out, the Earth Sun or the Earth Moon orbit is tilted about 5 degrees. Which, do I even have a protractor? Nope, I thought it was a long shot. Nope, I don't have a protractor. Maybe I'll get for one for the next time. 5 degrees is something like that. I mean, it's really tiny, but you can see that the moon is well above the Earth. So why is it that we get eclipses at all? Well, the reason for that is because while the Earth the tilt is, or the axis is tilted, that tilt is constant, or basically that tilt is constant as it moves around. As the Earth moves around the sun, the orbital tilt is going to stay constant in its orientation as it goes around like this. So it is almost impossible for me to do this in real time. But basically, the idea is that's not working. I think I'm going to need. I think I need to go away from physical props and go back to boring slides. So, all right, here we go. The moon's going away. No. All right, there we go. So, there we go. That one. Put that there. Entire screen. There we go. All right. So here's a diagram of what I'm talking about. Is that you have the plane of the Earth. If you look at the orbit of the Earth around the sun, that marks out a plane, and we refer to that plane as the ecliptic. And then you have the orbit of the Earth and Moon, and that is tilted with respect to this flat plane. And then that goes around like so. And the moon is orbiting around. So occasionally you will get an alignment. Oh yeah, I should look in. Thank you. I should really look into a GIF that shows this better. But as so let's look at two basic extrema. Here, if on the left you have the axis of No. Let's look at it a different way. So again, you have the tilt, or you have the plane of the ecliptic, and you have the plane of the Earth and Moon orbit. That Earth and Moon orbit is going to intersect that plane. And when those two planes intersect, so this would be this is the ecliptic, this is the orbit of Earth and Moon. When those two planes intersect, that point is what we call the line of nodes. So if we have such that on the left-hand side of this diagram, we have it so that the line of nodes is 90 degrees, pointed 90 degrees away from the sun. And so at new moon, in this demonstration, the moon is going to be well below the sun. It won't pass anywhere near, it'll be in the direction of the sun. It'll be close enough to the sun that you can't see it during the day because again, it's so bright, but it's not. It is not going to cover the sun in any way. And then commensurately on the other side, the full moon is a little bit higher up, and its shadow, it's going to pass well above the shadow of the Earth. But occasionally, you can have chance alignments. So now, if you go to basically the figure at the bottom of this plot or this diagram, what we have is that the line of nodes is now directly pointed at the sun. And so if the moon passes into the new phase or the full phase, when that happens, then you can have eclipses. So what we find is that for every year, there is at least 2 lunar eclipses and 2 solar eclipses that occur somewhere on the Earth, or that can be seen somewhere on the Earth. As I said before, a lunar eclipse, if you can see the full moon at the time that the eclipse takes place, then you can see the eclipse. So nearly half the Earth can see a lunar eclipse all at once. Whereas I hope I just illustrated that seeing a solar eclipse is a much rarer event, because the area or the location that you have to be in for this to happen is very small compared to, say, half the globe. So at least 2 lunar eclipses occur at some point in a year, and 2 solar eclipses occur at some point in the year. Sometimes you can sneak in a 3rd solar eclipse, but usually it's 2 and 2, the way the cycle works. All right, now. All right. I think I got sent something on Discord. Earth's Life has been sending me stuff. I will look at that. I will look at that video later, and I might come back live to comment on it. It's by 2 gentlemen, SE Montreal and Flatzoid, and how they understand how moons work. So that should be fun to look at. But before we go, and that actually took longer than I anticipated, let us switch topics a little bit, and let's talk about tides. So if you remember from our discussion of gravity, from a classical mechanics standpoint, gravity can be characterized as the force of attraction due between 2 masses, which is proportional to those 2 masses multiplied to each other and divided by the distance between them squared. So if you double the distance between 2 masses, the strength of the gravitational force is going to decrease by a factor of 4. So it decreases by what we call the inverse square law. Now, that actually does have real life consequences to objects in space, because objects in space are 3-dimensional objects. So one part of the object that is pointed, part of the moon that is pointed to at the Earth, is literally closer to the Earth than the point that is pointed away from the Earth. And so that even that small distance, even the width of the Earth, even the width of the moon, you can have tidal effects. You can see that sort of thing. So, so what I'm going to do here is I'm going to move this down. I'm going to pop that open. Open that up, and I'm going to add that to the screen. So let's look at tidal forces as seen from if we are a system of a system of 3 bodies on a spring, or a slinky. I don't know if any of you are old enough to know what a slinky is, but basically a spring. So what we have is, imagine you have 3 balls attached with 2 springs. So, and you let that system fall. What you're going to fall down towards the Earth. What you're going to see is that the gray ball in this case, or purple ball in this case, this ball, is going to accelerate faster than either the red ball or the blue ball because it is closer to the Earth, and so the force of gravity is appreciably larger than it is on either of the red or blue spheres, and so the acceleration is going to be larger. The red sphere is going to accelerate not as much as the purple, but it is going to accelerate more than the blue, because again, the distance is intermediate between the two. And finally, the blue is going to accelerate the slowest of the three. And initially, actually, at all times, but they're going to accelerate they're going to have different speeds. They're going to accelerate all at the same rate. No, I'm confusing myself. So, scratch what I just said. The purple ball does feel a larger acceleration because the force is larger. The red ball feels a intermediate force because the distance is intermediate, and then the blue ball the experience is a lower acceleration in comparison. So, hey Phil, howdy. Doing all right. Getting a little late for me, so I'm getting a little loopy. So what you see, in effect, is that as you drop, if I were to drop this slinky, then what would happen is that it would stretch. It would essentially elongate as I do so, or do that. And so when you're looking at it from my perspective, if you're looking at it from the Earth's perspective, if you're watching this system fall, then you see the purple sphere is accelerating faster, the red sphere accelerates intermediately, and then the blue sphere accelerates the slowest, and the whole thing stretches while it is moving downward. Now, let's change our perspective. Imagine you were sitting on the red ball, and before you got dropped, the blue ball was up here, the purple ball is down there, and suddenly the thing is released, and you are accelerating downwards with the red ball. What do you see? What do you see in terms of those balls? Obviously, you see the Earth rushing up to meet you and be your friend. But what about the other two balls? What you see is that to you, the blue ball, because it's not accelerating as fast as you are, is actually going to move away from you. It's going to appear to move away from you, and the blue ball or the purple ball is also going to move away from you down. What is that? Oh. What does that translate to in terms of the price of tea of China, in terms of tidal forces on planets or moons? Simple. You can kind of think of a planet or moon as being composed of sections, very much like those three spheres. And so this diagram can be, you can flip it either way. Here we're showing the tidal forces that the moon has with respect to the Earth, and you can easily flip that around. You can show that the moon is going to distort, is going to turn oblong in shape, based on the gravity that it experiences from the Earth. So in reality, both of these objects have been distorted gravitationally through tides, through this tidal action. And then on top of that, you've got both objects are rotating. We can experience this, or we see this effect most readily with ocean tides. Now, this is to first order. Ocean tides themselves, if you actually look into the specifics about when there's high tide and when there's a low tide in a local environment, it gets really complicated because land masses, the distribution of mass, really has an effect on how the water flows around the Earth's surface. So this is just really to first order. This is basically assuming that there really is no land, that there is just water. Water is more elastic than rock, and so that tidal effect that I've just been talking about can be seen to a larger extent on the water than it can be on the Earth. And so you get these what we call tidal bulges. If you're in essentially the rotation frame of the Earth and the Moon, you would see something that looks somewhat akin to this, and with a certain caveat, which I will talk about in a second. You will see that the water, if this is the spherical distribution of the water around the Earth, then you have a tidal bulge that is directed towards the moon, and then you have a tidal bulge which is directed away from the moon. But because friction is a thing, what we have is that it takes, because friction is a thing, this response, this bulging out, doesn't happen immediately. And it also, the Earth's rotation will carry that water around. And so you have this angle. The bulges are at an angle. And so you have, the straight line between the Earth and the moon. This bulge is going to be slightly offset to that. Let me table that for a moment. And let's just talk about high tides and low tides. If we just look at this diagram over here, hopefully you can see that because of the tidal bulge and because of the fact that the Earth rotates, someone on the Earth is going to experience 2 high tides and 2 low tides a day. And they're going to be roughly 6 hours away from each other. Again, when you get into the specifics of localities, it gets a lot more complicated, but roughly speaking, to first order, they're separated off by about 6 hours. And so you're going to experience 2 high tides in a day and 2 low tides in a day. Actually, oh, yes. There's something I wanted to do. Pardon me, guys. Bear with me. Do we have... No. Aha! This looks perfect. Stop sharing. Oh, wrong one. Share screen. Tide simulator. Boop. Wonderful what you can find on the internet these days. Okay, I agree. Actually, this is what I wanted. So again, you have the Earth going around, but that's actually not what I wanted to show you, because the Earth and the Moon are not the only 2 bodies in the universe. Ah, there we go. That's the one I was looking for. Da, 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 da. So we have, again, this is where we have the Earth, obviously, the tide, the exaggeration of the tides as brought upon by the moon. Now, if we include the effects of the Earth's rotation, you can see again that bulge has shifted, has rotated slightly. But then let us include the sun. So the sun is over to the right. The sun is going to exert a tidal force on the Earth as well, just not nearly as strong as the moon. That might seem a little bit counterintuitive because, well, the sun is way more massive than the moon is. But you also got to realize that the sun is way farther away than the moon is. And so again, gravity is a direct function of mass, but an inverse squared function of distance. So that distance, the fact that the distance goes over 1 over r squared, is really seen with this sort of example. It's the distance. The fact that the sun is so much further away is really diminishes the amount of tidal force that it applies, even though it's so much more massive than the sun is. And so we see here, hopefully what you can see is, I will stop it right there. All right, so really take a good look at this shape, where you have the bulge raised by the moon, and then you have the bulge raised by the sun. And so you have a fairly good bit of blue over here, a fairly good bit of blue over here. Obviously, the bulges here are larger because I said the moon's tidal forces are larger. But let me run it again. So now that was when the force of gravity from the Earth or from the moon and the force of gravity from the sun were counter to one another. They were at 90 degrees away from each other. Now, this is they're in line. So again, new moon and full moon have a special significance. In this case, when it's a full moon and a new moon, the gravitational force of the sun and the gravitational force of the moon are basically in line with each other, and so their tidal effects compound on each other. So here you can barely see that there is almost barely no bulge there at all, whereas the bulge that gets raised is much more significant. This is where you get the terms neap tide and spring tide. So a spring tide is when the high tide is, and the high tide is higher than it will. The high tide is at its highest extent, and the low tide is at its lowest extent. A neap tide is when that extreme of between high and low tides is smallest. So if you were to measure what the extreme between the height of the high tide and the low tide, what you would find is over the course of a month, that is going to, or over time, that is going to change. When the moon is full and when the moon is new, that extreme is going to be at its peak. The high tides will be exceptionally high. The low tides will be exceptionally low. When it's a neap tide, when when it's at right angles to each other, that extremum of high and low tides is going to get smaller. Now, as I said, once every day or twice every day, you're going to, in each day, you're going to have 2 high tides and you're going to have 2 low tides. In each month, you're going to have 2 spring tides and 2 neap tides. And so that is kind of the overview of tides, but there is an interesting sort of consequence to this. Stop sharing. So as I said, the moon presents the same face to us all the time. It is what we call synchronously locked. More strictly speaking, what that really means is that its rotational period is exactly equal to its orbital period. So its orbital period is 27.3 days, and so is its rotational period. Its rotational period is also 27.3 days. The reason for that is because over time, when the moon was created, up until when the moon was first created, as I'll go into next lecture, the moon was very rapidly spinning, but the tides that were raised on the moon were much more extreme than the tides that are raised on the Earth, because again, the force of gravity is mass dependent. Because the mass of the moon is so much smaller, the force of let me take that completely back. Because the mass of the moon is so much smaller that it can't basically hold itself as a sphere as tightly as the Earth can. So the tides were larger. What that means, or what that illustrates, and this is kind of the reverse of it, you can think of these bulges as handles. And so let me flip it around and basically talk about what's actually happening to the Earth at the moment. The Earth's day, the spin of the Earth, is not constant. When we say that the rotation of the Earth is 23 hours, 56 minutes, that is correct. But when you start, and it will be tomorrow, and it will be the next day, and the next day, and the next day. But if you start to look at the seconds involved, if you actually look at what the rotation rate of the Earth is down to fractions of a second, that changes constantly because the Earth is being slowed by the moon. Because this bulge over here is closer to the moon than this point over than basically the center point. And again, as I said, with gravity, distance is a big factor. Because that bulge is closer to the moon, it's going to experience a larger force. And if you apply and if you add up all the forces, essentially what that means is that the Earth is being pulled downward. It experiences a torque or turning force in the opposite direction of its spin, and so it's causing the Earth to slow down as we move on through time. Additionally, what it's doing is it's also causing the moon to speed up because again, gravity is reactive. It goes two ways. So this bulge is actually causing a force on the moon to accelerate it in its orbit. And so not only is the Earth spinning down, but the moon is getting faster, which means that it's getting farther away. So eventually, if getting rid of the scale, I broke it. Oh well. Let's rescale this. So if this were if this is the Earth-Moon distance now, over time, the Earth or the Moon is slowly getting away, moving away. I can't remember the exact. Oh, it's right there. A lunar month increases by 0.014 seconds per century, so it's not huge, but it is slowly getting away. Now, if the Earth-Moon system were to be allowed to evolve in this way for billions upon billions of years, eventually you get to a point where, as I alluded to in the last lecture, the two things are synchronously locked, or the two objects are tidally locked. They present the same faces to each other as they orbit around. So the orbital period of the Earth will also equal the orbital period or the rotational period of the Earth will also equal the orbital period of the Moon. So if you're on the Earth, if you're on the Earth at this time, when this happens, when this synchronicity or this tidal locking completes, then when you're on the Earth, you're going to see the Moon hanging in space all the time. It's not going to appear to move. It's just going to be in the same spot all the time. Basically, what astronauts would see on the Earth, or astronauts on the Moon saw, but the only difference is for them they actually saw the Earth rotating in the sky. But in this final event, in this final kind of scenario where you have complete tidal locking, both objects are going to present the same face to each other all the time, and they're going to basically be in the same part of the sky all the time. All right, let me go with that. Let's see. I've got a question. Is the center of gravity of the Earth-Moon system inside the Earth's radius? It is. It is. Again, I don't know the exact number, but it is fairly close to the Earth's core. So if you were to look outside the orbit, or outside the Earth and the Moon, and you were to look at them orbit, the Moon appears to orbit around the Earth, but in actuality, the Earth wobbles. So if you wanted to be very specific, then the Earth and the Moon orbit around basically a common center of mass, which is a point in space, and that point is slightly offset from the center of the Earth. We're going to revisit that when we get to talking about basically, well, actually, no, not in this class. I don't think I'm going to be talking about exoplanets in this class. So, although I might, who knows? And in that sense, I will talk about the fact that the sun, if you were to actually get up above the sun and were fixed in space, the point at which the center of mass between the sun and everything else in everything else in the solar system can actually exceed the sun's surface. So the sun would literally orbit around a blank portion or an empty part of the sky. So there we go. But the last things I will talk about in regards to this are that we see these tidal effects in other ways as well. Actually, I got ahead of myself. The most notable of which, or most dramatic of which in the solar system, was the Shoemaker-Levy 9 event. So we had this comet called Shoemaker-Levy 9. It was the ninth comet discovered by the observing pair Eugene Levy and Caroline Shoemaker. Shoemaker and Levy are two individuals. This is the ninth comet they found together. They were an observing team. And what they found was that when this comet was going through space, it got too close to Jupiter. And so that tidal stretching that I was talking about, that the moon raises the surface of the Earth up, it raises the surface of the water up. Well, it can get so extreme if the gravitational force is so powerful, it can actually rip things apart. So that spring that I was talking about would actually just rip apart entirely. Here, what we have is Jupiter, the most massive planet in the solar system, 300 times more massive than the Earth, and you have this little bitty comet flying through space, maybe a couple kilometers in size. It gets too close to Jupiter. Jupiter's gravity rips it apart, rips it into something like 12 roughly equal size cometlets, and it's really cool because then they all stayed in line. They all basically looked like ducks in a row and kept along in their orbit. But in the process of ripping the comet apart, it also changed the orbit of the comet, and it caused the comet to come back around and smack into the Earth, or smack into Jupiter. Shoemaker, Levy 9. I'm going to put this over here. I'm going to stop share screen. Yeah. So you can just Google it, Shoemaker-Levy 9. Here is an image taken by Hubble, I think, showing the incoming trail of comets right before it smacks into Jupiter. Here is an infrared image of those cometlets, showing them as red against the black background. And then, unfortunately for us, really, those impacts, it machine gunned against the Jupiter, but it did so on the dark side of Jupiter. We didn't really get to see the actual impacts because they were kind of hidden from view. But there was a satellite there that actually was able to take some images of, say, the after effects. And we could see the vast explosions that occurred because of these impacts, these repetitive, basically machine gunning of comet fragments into the surface of Jupiter. Maybe I'll do an entire show on that as well. But so tidal forces not only can raise tides. Tidal forces not only can raise tides on a solid body, can distort the physical shape of a solid body, can cause a body to slow down in its rotation or the orbit between two objects to get larger, but it can literally cause things to rip apart, to actually shred into bits. So I think that's where I'm going to leave off. Are there any other questions? I think there's center of masses and molecular time here. Center of, yeah. From a technical standpoint, yeah, we refer to that as the Berry center of the orbit, um, or the center of mass of the system. So yeah, rather than center of gravity. But yeah. So yeah, I'm going to leave it off here. And if you have any questions, please let me know in the chat. And while you're thinking up any questions that you might have, I will say, obviously, if you like this sort of content, please like, share, and subscribe. Um, if you would like to help me and and George Mason's outreach efforts, please consider becoming one of my Patreons. All proceeds go to our outreach endeavors, buying new equipment, paying the tour guides, paying for gas to get the tour guides from point A to point B, so forth and so on. So I hope this was enjoyable. I felt like near the end I was rambling a little bit more. But I hope this was enjoyable and informative in some way. So thank you all for spending your morning, evening, or afternoon, whichever it may be, with me. So, all right. All right. I think that's it. Oh, just as a channel announcement, I actually have to. The next thing I'm going to do, maybe not today, probably tomorrow, is I'm going to have another coffee and science, and I'm going to kind of eat a little bit of crow. So I've been telling flat earthers for a while now that there's this thing called the axis of evil, which is basically it's an alignment in the cosmic microwave background with our solar system. And so it would lead some to believe that that the solar system is preferential, that the universe essentially formed around the solar system. And I've been telling people it ain't a thing. The axis of evil doesn't exist. Well, it actually does. The axis of evil does exist, but there are caveats to that. And so the next Coffee and Science, SC Montreal was the person who brought to my attention this axis of evil. I asked colleagues of mine. I looked through my textbooks. I tried to find out what this axis of evil was. I couldn't find it. Right before I came onto the stream, I decided to do a little bit more Googling, and I finally found a credible source for it. I actually, not only that, but I actually found a scientific paper that addresses what this axis of evil might actually be. So that's going to be the topic of the next Coffee and Science. Is the Earth a special place in the universe from an astronomy point of view? So, all right. Peace out, clear skies, and I'll see you on the next one.